Alright folks, so we are doing experiment number 1 for lab number 8, and the first thing we did is we measured those resistors that we have over here. So this resistor over here is R2 that is going to ground. This resistor over here is R1 that is going to VCC. This resistor here is RD that is going to VCC. And this resistor here is RS that is going to ground. So based on the measured values, R1, which is this top resistor here, should be 1 meg. When I measured it, I got R1 will equal to 1.01 mega ohm. 1.01 mega ohm. R2, which is the one that goes to ground, this resistor over here, R2 supposed to be 470 k ohm. But I got 465 k ohm, 465 k. Then I have RD. RD supposed to be 20 k. I got 19.47 k. And I finally have RS over here, and RS supposed to be 10 k, and I end up getting 9.75 k ohm. So I measured those resistors, then I connected the transistor. As you know, the transistor is an NMOS, the ZVN2110A, and the way the connections go, it's always S. The first leg over here is S. The one in the middle over here is the gate, and then the third one over here is the drain. Before I move to the second step, I also measured the capacitances. So the capacitance of the gate is supposed to be 10 micro. I got 9.56 micro. The capacitance of the source should be 47 micro, but I got 39.4 micro. And finally, the capacitance at the drain gonna be 10 micro. I got 9.77 micro farads. Also, RL was supposed to be 100k. I measured it to be 97.3k. So the first step is to measure the component values. The second step is to measure the DC circuit. So to measure the DC circuit, I'm going to remove the capacitances. So none of the capacitances is connected to the circuit. All the capacitances are removed. I only have those 4 resistors, R1, R2, RD, and RS, which is what we call the voltage divider circuit. So what we're going to do next is we're going to apply the DC voltage source, and then we're going to start measuring the voltages at the 3 nodes of the circuit. So let's do that. Alright folks, so in the second step, what I will do is I wanted to measure the DC values. So I have connected a 15 volts to the top resistors, which what we call VDD. They are connected to R1 and RD. And I also connected the ground. So over here, I connected the ground to the source, as you can see here. And then I use the DMM. So this purple wire is the common, is the ground, and I'm connecting it to ground here. And the green wire will be able to measure the voltages at different nodes. Here I'm interested in 3 measurements. So the first measurement is the green line, and that's the source. So based on the design value, the source should be around 3 volts. So it's going to be a little bit off, more or less, but it should be around 3 volts based on the calculations that we have. So let's measure the voltage at the source and see what we have. So here the voltage at the source will equal to 3.19, roughly around 3.2 volts. So in step 2, I'm going to record that Vs will equal to 3.195 volts. And then I'm going to measure the voltage at the gate, and the voltage at the gate can be this blue line over here. So let's do the blue line. measure the voltage at the gate, roughly it's around 4.56 volts. I would say 4.568 volts, roughly 4.57 volts. And then I wanted to measure the voltage at the drain. The voltage at the drain should be close to the 9 volts. It's going to be a little bit lower because the voltage at the source was a little bit higher. That means ID was a little bit bigger than the 0.3 milliamp that we calculated. So here VD is 8.622 volts. And this is basically the second step. Alright guys, so at this point we end up connecting the rest of the circuit, where we end up adding the capacitors. So this capacitor will go from the drain to the load resistor, and the load resistor will go to ground, and then we will connect the capacitor at the gate, so it comes from the gate to the function generator, which is this leg over here, the function generator, and then this capacitor will go from the source to ground. Now keep in mind that when you connect the capacitors, those are electrolytic capacitors, so the polarities need to be well investigated. So the polarities for the capacitor at the gate should be that the negative polarity is at the signal generator. The reason is the voltage at the gate is roughly around 5 volts, 4.7 volts. So the voltage at the signal generator roughly 0, so it's more negative at the input of the function generator. You need to do that, otherwise the capacitor will pop up. It pops if you reverse the polarities, so pay attention to that. Anyway, so when we investigate the gain was a little bit higher than what is expected, so it has about 40% tolerance. And clearly that the gain here is a little bit higher, so you can see that the voltage at the output is 1.4 volts for 20 millivolts input. It should be roughly around 1 volt to get a gain of 50. So we need to lower the gain. There is two possibilities to lower the gain. One of them is to reduce the current, and the way you reduce the current is by making the resistor at the source bigger, and this will lower the current going through. This will lower the current going through the drain, and that basically will make GM smaller, because GM is proportional to the square root of the current. So basically, if I double the resistors, I will cut the current by half, and that will give me roughly around 70% drop in GM in the gain, and that's proportional to the gain. So that's what I'm going to do now, is I'm going to play with the source resistance until I get the proper gain, and once we get the source resistance, then we go back and we measure the DC values. So it's kind of iterative process. Design is always iterative process, and I want you to see that. So now we are going to change the resistor values for the source to 20K, and let's see what we get when we do that. So let's do that. So now we did make the source resistance to be 20K, close to 20 kilo ohm resistance. Now you can see that the gain dropped dramatically, that we have a gain of roughly 35 volt per volt. So we need a gain of 50. So it's clearly by making RS bigger, the current dropped, and because the current dropped, the GM dropped, and that made the gain lower. But here the gain was a little bit lower than what we expected. So now we're gonna adjust the source resistance to make the source resistance to be the 16.8K. So now when we made the source resistor bigger at 16.8 kilo ohm resistance, we got a gain within the range specified. So originally the design should be that RS going to be 10K and RD going to be 17.7K. So we said that let's be conservative, assuming that the gain initially going to be lower. We're going to choose the value of RD to be 20. And this way we can get a higher gain, and hopefully that we can get a gain of 50 plus or minus 20%. So it should be anywhere from 40 to 60 volts per volts. That's what the specs of the circuit was. So, and then we realized that the gain was higher than the range. Then we said that we need to lower the gain. So one way to lower the gain is by decreasing the current. And we can decrease the current by increasing RS. So we decided to do it using trial and error. So we said that let's make RS to be 20K. When we did RS to be 20K, that makes the current to drop to 1/2. That means GM dropped by a factor of 30%. It turned out that the gain dropped dramatically. We got a gain of 35 volts per volts. We didn't meet the specs. Then we said that now let's increase the drain current a little bit higher by choosing a value for RS between the 10K and the 20K. So we decided to add another 6.8K ohm resistor in series with the 10K, so that makes it around 16.6K. And based on that, we were able to get a gain of 44 volts per volts, 44.5 volts per volts. So as you can see here, I probably will be zooming in. Let me zoom in into the scope. Let's see if we can zoom in into the scope a little bit more. So you can see based on the measurements here, and I did do stop the capturing because I wanted the measured values to be accurate. So you can see that channel 1 is 20.4 millivolts and channel 2 is 912 millivolts. So channel 2 is the output, which is the blue line, and channel 1 is the input, which is the yellow line. So clearly that here we meet the specs, because the specs says that the gain should be between 40 to 60, nominal 50. So we got a gain of 44.5 volts per volts. Now keep in mind this was reached by adjusting the source resistor to play with the current. And this basically using this technique we did work with the circuit. Right guys, so now I'm gonna go back and I'm gonna measure the DC voltages again. They shouldn't change much. The only voltage I would expect to change would be VD, more change. So if we look at the measured value for VS, so VS now is 3.224 volts. And VG will be is the second one, which is the black color here, 566, so almost the same as the one before. And finally we're gonna measure the drain voltage, which is the orange wire here, and now it went up. So it's 10.7 volts. VD will equal to 10.69 volts. So clearly because the current dropped, the drain voltage will go up, that's expected. And we end up getting the gain voltage that we had. So the next thing I'm going to do is I'm going to save this data on my thumb drive, because we need this data as part of your report. What we're going to do in the next step is to investigate the frequency response of the system. So let me save this data and we will come back to do the frequency response of the system. Alright, so what we're going to do next is we're going to study the frequency response to find the low cutoff frequency and the high cutoff frequency. I already found the low cutoff frequency at 41 Hertz. By applying 41 Hertz, the gain was 70% of the mid-band gain. So you can see here that the gain is roughly around 70%. It fluctuates up and down a little bit because the scope is sensitive and all that. So by increasing the frequency, you're going to see that the gain going to increase slowly. Now I'm using the average here because the signal is noisy, but sometimes when we get a noisy signal from the scope, we're going to fluctuate between acquire and major, because acquire basically will make us trigger. Instead of averaging, we can trigger. So let me zoom in into the scope to show you how we can do that. So I'm going to zoom into the scope a little bit. So here I'm going to basically click on acquire, and then I'll do triggering, and you can see that the signal is noisy. So the measurement is not good. However, if you do the average, it will clean the signal, right? And this is here is at the time scale here is 10 milliseconds, which basically means that there is a lot of samples, right? But it's clearly that noisy. So when we wanted to increase the frequency, this is at 41 hertz, I'm going to start increasing the frequency. So what I'm going to do here is I'm going to do acquire, and then I will do sample. So you can see that the signal is noisy, and I will start to increase the frequency. So you will start to see that the gain will increase. So I'm going to start increasing the frequency now on the function generator. So this is at 50 kilohertz. You can see that start to shrink, and then the gain start to increase. Here I'm at around 150 kilohertz. Now what I'm going to do is I'm going to increase the scale. So let's increase the scale a little bit. The time scale, basically reduce it. I'm zooming in because I'm increasing the frequency. You can see that the gain is increasing, and I'm going to continue increasing the frequency. Now I'm going to start to increase it by the hundreds. So you can see that the gain start to increase. So now I'm around like 2 kilohertz. This is at 2 kilohertz. You can see that the gain is roughly around the 44 or 45 volts per volts. So if I do average, for example, and then I'm going to do major, that will give me a more accurate values. So the gain here is around 50 at 2 kilohertz. So in order for us to sweep the frequency, we have to go back to sample, which is the noisy thing. So now we're going to increase the frequency. The frequency is increasing. We start to see that the response start to be something like this. And that's basically what's the mid-band gain is. And you can see it's kind of flat now. It's flat, it doesn't change much. So now I'm around 18 kilohertz. That's at 20 kilohertz, it's a flat. It's dropping slowly dropping, but you know, that's at 67 kilohertz. So the higher cutoff frequency was found to be around 260 kilohertz. So now I'm at 73. I'm gonna move by tens. That's like 95, 105 kilohertz, so forth. I'm increasing the frequency. You start to see that the gain start to drop, and I start to get some noise here, right? You can see in this area there is some noise. To get rid of this noise, I have to do average. So if I do average, you see, we'll minimize that noise. So this is the gain roughly at 205 kilohertz, start to decrease. And then I'm going to go back to sample. I will go to 260. In fact, let me write it down, 260 kilohertz. That's exactly 260. And you can see that we have some noise. I'm going to do average, and you can see that the average, in fact, that let's increase the average to 160 samples. That's a better average. It takes some time to clean it. And now we're gonna do measure. And you can see that this is roughly around the 70% of the volt per volt gain, more or less. Yep, it's about 640 at 20 milli, more or less. This is the 3 dB cutoff frequency at the higher end, around 260K. If you increase it, it's going to keep dropping. So let's go back to acquire, sample. You can see that's noisy. We're going to focus on the blue line. By increasing the frequency more, you can see start to drop. This is like very high frequency. This is at 1.4 megahertz. Now keep in mind that our breadboard start to degrade around 500 kilohertz, but it will handle 1 megahertz. But you can see that the response dropped dramatically at 1.4 megahertz. So clearly that this amplifier will have mid-band gain, and then has low cutoff frequency around 40 hertz, and then we have high cutoff frequency around 260 kilohertz. The low cutoff frequency is caused by the coupling capacitors. The bigger the coupling capacitors, the smaller the cutoff frequency going to be. And the high frequency cutoff is caused by the internal capacitance of the transistor and the parasitics, the stray capacitances of the breadboard. So, which are very, very small capacitances. So, and this is a very good practical hands-on experience to how the circuit will work. Now what I'm going to do is I'm going to collect data at different frequencies, and I will come up with a plot, and I will be able to provide you with this data so you can see it as part of the data. And then we're going to go to step number 8. So in step number 8, you basically wanted to investigate the clipping of the signal. So what we're going to do is we're going to go back to 10 kilohertz. So I'm going to click 10 kilohertz here, and now I'm going to come to the time. I want to show some time here, and we're going to basically increase the input voltage until start clipping. What I'm going to do now is I'm going to start to play with the input voltage. So I'm going to increase it. So now it's at 30 millivolts. Let's reduce those. And this also, so the yellow line is your input signal and the blue line is your output signal. I'm going to start increasing the input voltage at 10 kilohertz, and we're going to keep increasing it. And let's play with the scale. Let's play with the scale one more time. So you start to see that there is some form of clipping at the bottom and another form of clipping at the top. So it clips at the bottom and clips at the top. And what I'm going to do now is I wanted to measure the voltage as DC coupler at the drain. So I'm going to come to the drain, and I'm going to measure it at the drain to show you the DC coupling. And now I'm going to click on channel 1. I'm going to do DC coupling because I want to measure the AC and the DC. Let's stop that and let's see what we have, and let's see where will it clip from the bottom and from the top. So I would expect the voltage at the top will click very close to the VCC, which is the 15 volts. It's going to be a little bit lower than that, and then at the bottom it's going to clip very close to VS, the source voltage. Now remember, the source voltage was around 3.2 volts. So I'm going to use the cursor to determine the clipping from the top and from the bottom. So let's go to cursor, and we're going to say it's on, and this amplitude. So cursor 1, I'm going to move. Yeah, let's delete this channel 1. Let's just do channel 2. So I'm gonna move, we're gonna do cursor amplitude channel 1. I'm gonna move the top cursor on the top, and that shows around 14.2 volts, as you can see here, 14.2 volts. I'm gonna move to the second cursor, and I'm gonna do it at the bottom, and that's roughly around 3.8 volts, right, more or less. So usually the transistor will clip from the bottom when it enters the triode region, and it will clip from the top when the voltage is very close to VCC, because when the current is very small, the transistor is not amplifying anymore. So it's a clipping from the top and from the bottom, and the bottom it enters the triode region, and the top the current is too small. GM is very small, that it doesn't give you a very good amplification, so it clips from the top and the bottom. This is the voltage at the drain. You need this data also, so make sure that you understand this concept of clipping. Why does it clip from the top and from the bottom? So this is the end of the first experiment, and I'll be able to provide you the frequency sweep data for the frequencies, and then you can basically plot them and all that as part of your report. Thank you so much for the first experiment. We still have 2 more experiments for this lab we're going to do, so thank you.